right, so this is going to be a fairly straightforward section. We're talking about section 4.6 here. And in section 4.6, we're going to take a look at a summary of curve sketching. So we're going to use all that stuff we learned in chapter 4 about increasing, decreasing, extrema, concavity, all of that stuff to make a good graph, to make a good sketch for a function. Now this section used to be really, really important back in the day, back in the dark ages, before we had technology that could make all these graphs for us, and we had to do all of our graphing by hand. You had to go through all of these steps to make this happen. Now with technology, it's changed the game a little bit, and we can just type some quick notation into Desmos and it can graph it for us, or a calculator or some other website. There's lots of them out there. So we need to change how we think about things, but we can still use those same techniques to make sure. And what I'm talking about here is we need to be able to make sure that we're seeing what we think we should be seeing when we take a look at the graph of a function on some sort of graphing tool. Okay? Both of these graphs down here are the same function. They're that cubic function right there. But depending on the window you look at, you might be mistaken in what you're seeing. Like the graph on the left makes this thing look like it might be a parabola, just because of the way that window is. It also makes it look like it's way above the x-axis. Now the graph on the right is the same graph, and that highlighted area is this little tiny peak right there. Because with a different scale, a huge peak can look really small. Right? And since that minimum is so low compared to that tiny little maximum, right? A different viewing window can make the graph look really different. So what we're going to take a look at is those tools that we used to use to graph things and how we can make sure that we use those to get a good viewing window of what we want to see for our graph. Right? So the guidelines for this are: find the domain and range of the function, determine if it has intercepts, asymptotes, or symmetry, and then use that first derivative and that second derivative to find extrema, increasing and decreasing, points of inflection, intervals of concavity. And then put that all together to say, okay, here's a good viewing window. Here's what I want to see when I look at this graph. We only have one example. It's right here. And so we're going to analyze the graph of the function f of x equals 2 times the quantity x squared minus 9 divided by the quantity x squared minus 4. All right, first things first, domain. Since this is a rational function, I know that I'm going to have issues if that denominator is ever equal to 0. So when will that denominator, x squared minus 4, ever be equal to 0? And that's going to be when x is equal to plus or minus 2. So I know that my domain is going to be negative infinity to negative 2, union with negative 2 to 2, union with 2 to infinity. Okay? Now, I dislike that they say find the range next, because it's difficult to find the range next. The range should be found later on, so we'll come back to the range. So we'll come back and find the range later. Okay? All right, after domain and range, they want us to talk about intercepts, asymptotes, and symmetry. So let's check and see. Does this thing have any intercepts? That is, does it have any x intercepts or any y intercepts? Okay, so I'll do all my scratch work over here on the right. X-intercepts are when the graph crosses the x-axis. When the graph crosses the x-axis, effectively y is equal to 0, or the function is equal to 0, if you prefer. Given that our function is a fraction, the only way for a fraction to be equal to 0 is if that numerator is 0. So we're going to say when is 2 times x squared minus 9 equal to 0, and that's going to be when x is equal to plus or minus 3. So I know I'm going to have intercepts at negative 3 comma 0, as well as at, not union, that would imply that these were some sort of intervals, at 3 comma 0. Okay. How about y-intercepts? Let's see. Y-intercepts are when x is equal to 0, because it crosses the y-axis. Setting x equal to 0 in our function, we're basically finding f of 0, and we're going to get 2 times negative 9 divided by negative 4, which gives us 9 halves. Or if you prefer 4.5, I like 9 halves better. So I'm just going to say that that's 0, 9 halves. So there's my intercepts. Does this thing have any asymptotes? Right? Now, in terms of asymptotes, there are two types. There are the horizontal asymptotes and the vertical asymptotes. There's also slant asymptotes, but we don't have any of those here. Slant asymptotes occur when the numerator is exactly 1 power higher than the denominator, and since we have an x squared over an x squared, there's no slant. Okay. Whew. Horizontal asymptotes. Horizontal asymptotes are answering the question, what is the limit at plus or minus infinity of our function? And when x gets really, really large, either positive or negatively, because of that squared there and there, those two binomials are essentially going to cancel each other, and we get a horizontal asymptote, or a limit at infinity and negative infinity of 2. Right? Now, vertical asymptotes are when the denominator is going to be equal to 0, which is at positive and negative 2. So we're going to get vertical asymptotes at negative 2 and at positive 2. Right? Symmetry. Does this graph have any symmetry? Well, there are two types of symmetry we're interested in, even symmetry and odd symmetry. Even symmetry is when f of x is equal to f of negative x, and odd symmetry is when f of negative x is equal to negative 1 times f of x. Okay? Now, given that both of our powers are squareds, the only possibility here is going to be even symmetry, so I'm not even going to bother checking odd. So what is f of negative x? Well, f of negative x is going to be 2 times negative x squared minus 9 over negative x squared minus 4, which is just f of x after you clean it up. So this thing is an even function. Okay? That means it is a perfect reflection across the y-axis, which will help us graph this thing. Okay? All right, so now that I'm technically done with 1 and 2, which are really college algebra for the most part. I mean, I did use limits to find our horizontal asymptote, but you don't need them to do it. There are some rules that you could have used from college algebra. Now let's take a look at calculus, which is going to be step 3. All right, so in step 3, I want to find increasing, decreasing, maxes and mins, concave up, concave down, and all that. So I'm going to need my derivatives. So if my function f of x is the function 2 times the quantity x squared minus 9 divided by x squared minus 4, what's f prime, the first derivative, going to be? Let's see, that's going to be the bottom times the derivative of the top, which is going to be 2 times 2x minus the top, 2 times x squared minus 9 times derivative of the bottom, which is 2x over the bottom, the denominator, x squared minus 4 squared. Cleaning up that numerator a little bit, we're going to get 4x cubed minus 16x minus 4x cubed plus 36x over x squared minus 4 squared, which is going to give us, after we clean it up a little bit more, 20x upstairs and x squared minus 4 squared downstairs. Okay? And there, that is going to be our first derivative. And so then that first derivative is going to give us increasing and decreasing as well as extrema. Now, I hope you're seeing what I'm seeing. I hope you're seeing that that denominator, I'm going to make it a little more clear. No matter what value I use for x, that denominator is always going to be positive. So that means that the numerator is going to run the show. All right, so critical numbers. Critical numbers are when the first derivative is equal to 0, or when the first derivative does not exist. Okay? That's going to give me several intervals to test. Right? When I test those intervals, right, like say -3, now remember, denominator is always positive, so that's going to give me a negative value there. -1, denominator is always positive, -1 in the numerator makes the numerator negative, derivative is negative, positive 1. Denominator is always positive, makes the numerator positive, and 3 positive. So it looks like we are decreasing from negative infinity to negative 2, union with negative 2 to 0, and we are increasing from 0 to 2, union with 2 to infinity. Now, if you're wondering why I didn't combine those and make that one big interval from negative infinity to 0, it's because at negative 2 there's a vertical asymptote. And so there is a discontinuity. Negative 2 is not in the domain of the function, so I can't say it's decreasing at a value that's not in the domain of the function. It doesn't work like that. All right, how about extrema? Well, the only candidate for an extrema is 0, because that's the only place where the derivative changes sign. It goes from negative to positive, from down to up. So I think we have a minimum there. We have a minimum when x is 0, which happens to also be the y-intercept, which you already found to be 9/2. Right? Now we need the second derivative so we can get concavity. Right? So if f prime of x is 20x divided by x squared minus 4 squared, then what will f double prime, the second derivative, look like? Well, again, we're going to have to use the quotient rule. So we're going to have x squared minus 4 squared, the denominator, times derivative of the numerator, minus the numerator, times the derivative of the denominator. Let's see, that's going to be 2 times x squared minus 4 times 2x, chain rule, divided by the denominator, squared again, so that's a fourth power. Now it looks like there's an x squared minus 4 and x squared minus 4 and x squared minus 4, so I should be able to factor that out, which will then give me 20 times x squared minus 4 in the first term, minus 80x squared in the second term, when I factor out that x squared minus 4, divided by x squared minus 4, and now it's cubed. Cleaning up that numerator further, I am going to get negative 60x squared minus 80 divided by x squared minus 4 cubed. Right? So my second derivative is negative 1 times 60x squared plus 80 divided by x squared minus 4 cubed. Now, if you're wondering why I did this, there's a reason. Right? I wanted to show that no matter what number I put in for x, inside the parentheses will always be positive, and that negative 1 means that numerator will always be a negative number, because that's going to help me evaluate. Okay? All right, first things first, though, I need to find out when is the second derivative equal to 0, or the second derivative, when does it not exist? Now, I just got done saying the numerator is always negative, that there's no way to make it be 0 then. So the only way for this thing to have any importance is for the denominator to not exist, and the denominator doesn't exist at 2 and negative 2, as we've established several times already. All right? So that gives me 3 intervals to test. Now, since the denominator runs the show, that is, the numerator is always negative, the value of the denominator is going to tell me whether this thing is concave up or concave down. On interval number 1 over here, like let's say we use negative 3. Negative 3 squared is 9, 9 minus 4 is 5, 5 cubed is a positive number. Denominator is positive, numerator is negative, second derivative is negative. Interval number 2, if I choose 0, plug 0 into the denominator. 0 minus 4 is negative, negative cubed is negative, numerator is negative, denominator is negative, negative divided by negative is a positive. Interval number 3. I'll use the number 3. 3 squared minus 4 is positive. Positive cubed is positive. Numerator is negative. Denominator is positive. We're negative. So now what does that tell me? Well, where are we concave up? Well, we're concave up from negative 2 to 2. And where are we concave down? Well, we're concave down from negative infinity to negative 2, union with 2 to infinity. And what about inflection points? Okay. Well, concavity changes here and there, so do we have any inflection points? No, because even though concavity changes, negative 2 and positive 2 are vertical asymptotes. So it changes when you move across the vertical asymptote, but it does not actually have a, what am I looking for there? An inflection point at that point, at negative 2. Okay, so I think we've done everything we need to do, right? Yeah, we found intercepts, asymptotes, symmetry, domain, range. Oh, we haven't found range yet. We'll come back and get that. And extrema and points of inflection. So now we should be able to put this all together and make a graph of this thing. Okay, first things first. Let's put the known points on this graph. Known points are our intercepts. Okay? We have intercepts at negative 3 and positive 3 on the x-axis. And at 4.5, 9 halves on the y-axis. Now let's put in those asymptotes. I know I have a horizontal asymptote at 2. And I know that I have vertical asymptotes at 2 and negative 2, right? I'm trying to remember. I'm going to go back and just make sure I got that all right. Let's see. Yes, 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 yes. Okay, we're good there. Right? Let's see. Now let's take a look at describing the behavior. Right? Decreasing from negative infinity to negative 2, and then again from negative 2 to 0. So out here, we're a decreasing function, and in here, we are also a decreasing function. Right? We're increasing out there. So we're increasing here, and we're increasing here. Right? Minimum. So this is a minimum right there. Right? What about concavity? We're concave up in the middle, concave down outsides. So out here, we're decreasing and concave down. Out here, we're increasing and concave down. And this entire interval, we are concave up. All right, let's see if we can draw this picture now. Okay, so out here, I'm going to just number these real quick so we can talk about them easier. I'm going to call this part 1 of the graph. That's left of that vertical asymptote. I'm going to call this part 2 of the graph. That's between the two vertical asymptotes. And I'm going to call this part 3 of the graph, which is to the right of that vertical asymptote. Out there on part 1, I have a decreasing function that is concave down and passes through the known point of negative 3. So I have a decreasing function that is concave down, has 2 asymptotes, something like that. Decreasing, concave down, looks good. Okay. On piece 2 of the graph, between the two vertical asymptotes, I have a function that decreases, that increases with a minimum of 9 halves and is concave up. Decreases, then increases, concave up. And then out there on interval number 3, on part 3 of the graph, I have an increasing concave down function that passes through that point and has 2 vertical asymptotes. And there's what my graph should look like. Now, if I go over here to Desmos and graph this exact same thing, I should see that f of x is equal to 2 times the quantity x raised to the second, was it minus 9? Divided by x raised to the second minus 4. We said that we had a vertical asymptote at negative 2. We said that we had a vertical asymptote at positive 2. And we said that we had a horizontal asymptote at positive 2. Let me make that projector mode so it stands out. And there's our graph. We have a minimum of 4.5, 9 halves. Intercepts here and here. Okay. Is that the same thing we came up with? Sure. I mean, I would prefer to use Desmos all day long because this took 20 minutes to do. Right? So, section 4.6. The idea behind section 4.6 is something that is kind of a holdover. We don't use it too much anymore. But this process that we just went through was how graphs used to be made. It was how we did things. We had to do it that way. We didn't have any way to make the graph of a function any way other than doing everything by hand. And so if you wanted to know a good graph of a function, if you wanted to know what this thing looked like, that is the process that you would go through. Which seems brutal, mostly because it is, but at the same time, it's kind of magical that you can do all this work and you can use that just to find what this graph looks like, that the math can tell you if you know how to interpret what it's saying. All right, that's it for section 4.6. I hope that you learned two things in section 4.6. One, I hope that you have an appreciation for what calculus can do in terms of just something as simple as describing a graph. And I hope that you have a really good appreciation for Desmos or your graphing calculator, for what it can do for you to make your life so much easier when it comes to graphing. This is why when I say I love Desmos, I mean I love Desmos. Because I remember doing this and having homework sets where you would have to do 2 or 3 of these. And 3 problems can take an hour, easily. Sometimes 2, depending on how nasty those are. All right, that's section 4.6. The next video will be section 4.7. Have a wonderful day.